What's the most famous formula in physics? Equals mc squared. So,
isn't it also plus bc squared?
yeah, so this is number 4, radioactive decay review. So Einstein didn't start with E equals mc squared. He started with E squared equals P squared C squared. What this means is that if you have a particle of matter that is not moving very quickly, it has no momentum. P is for momentum, right? So this becomes 0. So for kind of everyday matter, that has mass but not a lot of momentum, E equals mc squared. That's sounds simple, but it's really very deep. It shows truth about our universe. We teach you in junior high all the way up that matter is matter and energy is energy, right? But really, mass and energy are different forms of the same thing. And we can translate one into the other, and that actually happens all the time. We're not doing this side right now, but if you have something with no mass that does have momentum, which is possible, what has momentum but not mass? Good. So for photons, and we're going to come back to this when we do quantum. The energy of a photon is its momentum times the speed of light. And we'll get into that more later. But right now we're going to look at this one. So for matter that's sitting still, it has energy in it. And of course, in a nuclear power plant, we can get lots of energy out of a little bit of matter if we just translate some of it, right? What is the process by which we get energy in a nuclear power plant?
Isn't it?
It's fission. So fission is splitting apart, right?
How does making one make more energy?
So how come we just recently did the first net positive fusion reaction?
Is fusion just making a new one?
Fusion is taking two things and putting them together.
How does that make more energy?
So how do we get energy out of fusion and energy out of fission? The answer comes in the size of the nucleus.
Increases, so like the energy comes up.
Yeah, that's right. So for small nuclei, when you put them together, because the binding energy per nucleon is different, which is what we're going to learn right now, when you fuse small nuclei, you get energy out. But for big nuclei, it takes energy to put them together. That actually would take energy in. And so for a big nucleus, when it falls apart, you get energy out, which is fission.
So fusion's just small stuff?
Fusion is small stuff. That's right.
So for the equation, E equals mc squared, so m is mass, right?
Yep.
So, but do you take the difference of mass?
Yes. Whatever mass is turning into energy.
So, wait, what? Okay.
I'll show you. Okay. First of all, we have to define something, an AMU. What does that stand for?
Atomic mass.
Atomic mass unit. What is an atomic mass unit?
12 carbons.
Good. I don't know why they didn't choose hydrogen, but it's carbon. We chose carbon and we said carbon 12 is 12 atomic mass units. Exactly. No change. So why C12?
God.
Bees. Just say bees. That's the reason. We don't know why. But that's That's the answer. Okay, now, if you weigh carbon and you get the mass of a carbon-12 in kilograms, you'll find it is 1.98998 times 10 to the negative 26 kilograms.
Bees?
Bees.
That's the mass of bees?
No, that's the reason. Bees is the reason for the mass. This is the mass of one carbon-12 nucleus in kilograms. And we just said bees is the reason we chose carbon-12. I don't know why we chose it. And so if you chop that into 12, you'll get the mass of one atomic mass unit in kilograms. Does that make sense?
Do we need all those things?
Yes, we do actually.
You can't just say it's two?
No, no, you can't. We did for a long time, but that was before we realized that this was happening. Okay, so we actually have to have quite a bit of significant figures for this. Okay, so I'm going to try to show you the amount of energy in one atomic mass unit.
So you divide that by 12 to get 1 energy.
Good. So we got to divide this by 12 first. And what's that going to give us? So do this on your calculator. So you do 1.98998 times 10 to the 26. Divide that by 12. And you should get somewhere around 1.66 times 10 to the negative 27. That sounds familiar, right? But let's go a little bit more significant. So this is the mass in kilograms of one atomic mass unit. We do that because we want to find the E from E equals mc squared, and in physics the m is in kilograms. So now we want to take this mass and we want to multiply it by the square of the speed of light. So we take our 165,832 and we multiply by the speed of light, which, if you take it to a lot of significant figures, is 2.99. It's 9979. Yeah. Let's go 9979 times 10 to the 8. I think it's 99795. And this is meters per second. No. And we got to square it, right?
Kilogram meter per second squared.
Meter squared per second squared.
Yeah, well, yeah.
It just goes to the 16th, so it's still like negative 7.
If you do that, I think you're going to get 1.49 times 10 to the negative 10.
Oh my god, how did I get that?
It's 1.4904, I think.
In one atomic unit.
Yeah, when you
Then to the
This is joules, right? So this is now our energy in joules. And you're right, it doesn't sound like a lot, but as Roham says, only one atomic mass unit, right? So it's actually a lot of energy.
So how much would carbon 12 be? 12 times that?
Well, so we're gonna get there. This is the energy in joules. It's kind of an awkward number. So we're gonna turn this into electron volts. So we're gonna divide this by the number of joules in an electron volt. Does anybody know the answer? Does this number look familiar? This is the charge in coulombs of an electron or a proton. It's also the number of joules per electron volt. So if we divide that I tried to times it last class.
This equals electron volt.
Exactly. We're gonna flip this up and we're gonna get the number of.
Wait, but I thought it was the difference in mass, so why did we use 1.65?
We haven't gotten to the difference yet. We will.
Oh, okay.
We will. I think if you do that, you'll get 9.315 times 10 to the 8 EVs. Yes.
So what's the significance of electron volts? What's the
We're getting there. We're getting there.
Would this still be energy though?
Yes. Okay. So 931.5 mega electron volts. This is a number you see a lot.
Look, I've seen this.
And this is an energy, right? The energy of what?
An electron volt.
Well, it's in mega electron volts. But what did we just do? What this energy is from what?
Energy for 1 MU.
Good. This is the energy per 1 atomic mass unit. Okay. This is very handy to have this number. If you try to do this process on the exam, it will take you too much time, and they know it's going to take you too much time. And so it's nice to have this number in your back pocket, so you can just take the number of atomic mass units of the element you're working with and just times it by 931.5, and instantly you have mega electron volts.
No, it's just an easy number.
So this is the rest energy, we call it.
Energy was rested.
So say you wanted to find the amount of energy in a carbon atom,
This is the defect.
you would just take this times it by 12, and you would have your mega electron volts. And so if that whole carbon nucleus went into energy, you would get all those mega electron volts of energy. Now here's the weird thing. If you want the mass, us physicists being inherently lazy, say, well, if we want mass, we can just say that it's 931.5 mega electron volts per c squared. It's the same number. And this is our rest mass.
How did you get that?
I just put the c squared underneath the MEVs. That's the number. So basically, if I divided this number by speed of light squared, I would get the mass in kilograms, right? But we don't want to have to do that every time. So we just say that same number is the energy of the particle, and if you put it in MeV per c squared, it's the mass of the particle as well.
But c squared here isn't part of the units, it's the...
This c squared is part of the unit.
But isn't it 3 times...
Instead of saying mass in kilograms, we say this is the mass in mega electron volts per c squared.
But reality is like divided by the speed of light squared.
If you wanted to find it in kilograms, yes.
Yeah.
Well, actually, you'd have to change this into joules first, then divide by c squared. Okay, so give me a element, any element.
Carbon 12.
No, carbon 12 is boring.
Nitrogen.
Nitrogen?
Uranium.
Let's do nitrogen 14.
Isn't that normal?
Look it up in the Giancoli. Turn to page 1064. It's almost at the back. This is a list of isotopes, and you'll see for nitrogen, it lists nitrogen 13, nitrogen 14, and nitrogen 15, and it gives you an atomic mass. Now, you'll see on the periodic table, if you look at the back, nitrogen says for a mass 14.00674. And here, it says nitrogen 14 is 14.003242. They're different numbers. So what's the mass in the periodic table? That's the average of naturally occurring isotopes. That's not what we want. We want the actual mass of nitrogen 14 specifically. And so that's here. So, and this is 7, right? So that nitrogen mass is 14.003. No, 074. You're already looking at the periodic table?
No, I'm looking on the gene pool.
Am I not seeing it right? Nitrogen 14.
Oh, there's 214.
No,
There's carbon
No, you were
You're looking. This is carbon. Yeah,
I
that's
was
carbon.
looking at the one above.
Yeah, that's carbon. Okay, so this is the AMUs. Okay, so tell me the energy in a nucleus of nitrogen 14.
So just times that by 9
You got it for us. You got it. Just times this by 931.5. That's the mega electron volts per AMU, and we'll get the mega electron volts per nucleus.
And then to convert it into joules, you times it by 1.6 to the negative 19.
That's right. Okay, now, let's find the difference. So the mass of a neutron, if you look on the very top of that list on page 1064, the neutron is 1.008665 AMUs, and a proton, which is H11, is a proton. It's the second thing, and that's 1.007825.
Wait, neutrons decay?
Okay, add up for me the mass of the pieces. So if we take, this is the last thing we're gonna do. If you took apart this nitrogen, how many protons would there be? 7. So times this by 7. And how many neutrons would there be? 7. And times this by 7. Add them up and give me the total.
Only 14.003079.
No, it's not. It's not. You got it? 14.11543.
Why is it different?
And up here we have 14.003074.
And then you take this difference.
So this thing that Tamer did so nicely for us is the parts of N14. And this is the actual mass of the nucleus of N14. What do you notice about those masses? They're different. Which one is bigger? The parts are bigger. The difference, if we subtract those,
Well, what's adding the weight?
Oh, those are electrons,
no, the electrons are baked in, don't worry about that. The difference here is 0.11, I don't know what the difference is. Can somebody subtract it for me?
0.112356.
2356? Use. And if we multiply that by 931.5 mega electron volts per AMU, we will get an amount of energy. Somebody do that for me.
104.6 or 104.7.
104.7?
Sure.
Okay. That is the energy difference between nitrogen 14 as a nucleus and nitrogen 14 as all of its parts spread from the nucleus. Exactly, thank you, Alex. So this is called the mass defect. And it is equal to the binding energy. And I'm sorry I'm taking you into the break here, but I think it's worth it. So this is really important to see and understand this, that when you put particles together into the nucleus, you end up with less mass than you had before. The atom weighs less than its parts. This is the binding energy. So repeat after me. Binding energy is the energy that the nucleus lacks. Good. So it's like if you were rolling a car along a slope and it went into a dip, it would go down into that dip and stay there, right? That's what's happening with all these pieces. They have this energy, and when they collapse together, they're at a lower energy. And that's what makes them stable. They stay together because they're stable. So that's the binding energy. Now the last thing, sorry. There's a diagram. Miss it here. It's on like 940 something. Sorry. I'm gonna make you stay for this because I'm looking for fusion and fission. There it is. It's on page 920. And it looks like this. Remember I asked you the question of why do we get energy out of fission and fusion? This is a graph of binding energy per nucleon. If you have small nuclei, when you split them apart, you get a higher binding energy, which means when you put them together, energy is released. But above, somewhere around nickel up here, it starts to get less. So when you have uranium, when you split it apart, you get a higher binding energy per nucleon. And that's why with big nuclei, you get energy out when you split them apart.
So is that why fusion is better?
That's why, well, fusion is better because these are radioactive and these are not.
As in because it releases a lot more energy.
So you can do fusion with seawater and you have no toxic products. All these products are still radioactive, so they're dangerous. I'm sorry, I pushed you to this. You'll have time tomorrow.
Trying to have a spare 5 minutes.
Have a wonderful weekend. I will give you some problems